Oh, okay. Okay. If has anyone found a phone in this room? Someone lost a phone in this room. So, and we're not going to start until the phone is found. This could take years. No. Okay. Let's start. Thank you for showing your support to group-based proofs in these hard times in coming. We're happy to have Hossein Hafezi to tell us about KZH-Fold, the very cool scheme.
Is it? Oh, it's on. Yeah, hey everyone. So today I'll be talking about KZH-Fold. This is joint work with George, Arancha, and my advisor, Benedict, previous advisor, technically Benedict. All right, I have loads and loads of preliminaries to review. So first I'm going to talk about what is a NARC. Obviously you all know it, but I still have to go through with it for the sake of completeness, which is a non-interactive argument of knowledge. So imagine we got a public relation R, which is an MP language, and we have two parties here. We got a prover and we got a verifier, such that they both have an instance X, and only the prover has a corresponding witness W. Here, the prover sends a proof to the verifier, such that it proves that it knows the satisfying witness, basically knows W, such that it satisfies completeness, meaning if the prover is honest and W is indeed a satisfying witness, then the verifier will always accept. Knowledge soundness, meaning if the verifier accepts, then the prover must indeed know a valid witness. And finally, a NARC is called a SNARC if it is sync-synced. As in the size of proof is sublinear in the size of W. And let's quickly see what an accumulation scheme is. So imagine we got two MP languages, L and LAC, and we have an instance of L and an instance of LAC. An accumulation scheme at a high level reduces satisfiability of an instance of L and an instance of LAC into a single instance of LAC, such that it is a reduction of knowledge, meaning that the result of the accumulation is going to be in the language LAC if and only if the initial instances were in L and LAC. And the intuition is that it reduces two NP instances into a single one, and we'll actually see why it is useful for us to build recursive proofs. And let's quickly see what is incremental verifiable computation, or IVC. So IVC is used to prove correctness of iterative computations, like the one you see on the diagram. In an iterative computation of a function f, input to each step is the output of the previous step, and every step can also take a non-deterministic witness as well. And PCD is a generalization of IVC from a straight line to a directed acyclic graph. For example, imagine your steps of computation are in the leaves, and the internal nodes, you have a tree, and the steps of the computation are going to be in the leaves of a tree, and your internal nodes for the tree will be recursively basically verifying the computation for the children. And the point of PCD compared to IVC is that it enables parallelism and distributed proving. And it has like applications in distributed proving, such as distributed signature aggregation, secure aggregation, and etc. I'll be actually talking a lot about these applications soonish. So, but before that, let's see how we can build IVC or PCD. So the traditional, when I say traditional, it means like for 10 years ago, I think, the way to build an IVC or PCD scheme is that we build an augmented circuit, which consists of the original function f, which is subcircuit f, and also a snark verified subcircuit, which we call this the recursive overhead, such that the point of the snark verifier is that it will verify a proof of correctness for the previous step of computation. And there was a line of work starting from Halo that they observed that the snark verifier is quite expensive to be implemented in the circuit. And they proposed a new approach, which is building IVC or PCD from accumulation schemes. The high-level idea is that we defer checking all those proofs, pi-i's, to the last step of computation. And what we do, instead of checking them at every step, we sort of like accumulate or aggregate them and defer them to the last step of the IVC. And if you want to get the intuition how it works at a high level, we replace the snark verifier here with an accumulation verifier. And all the proofs are accumulated with a running accumulator, So after n steps, we're going to get a accumulator x sub n, which is valid if all the intermediate proofs pi i's were valid. And the whole point of it is that the accumulator verifier is way more efficient than the snark verifier in the circuit. And this is basically formalized with the BCLMS compiler, which says if we got a NARC, an accumulation scheme for the NARC verifier, then we can build an IVC or PCD scheme with the following properties. So the IVC proof is going to be equal to the accumulator size. The IVC verifier is going to be equal to the decider, or the satisfiability function of the accumulation scheme. And finally, the IVC prover time is going to be equal to the prover time of the NARC plus the prover time of the accumulation scheme. And if I want to give you a summary, there's a really long line of work over the course of 5 years on different accumulation schemes from different primitives. It has started by using Peterson as the underlying commitment scheme, and then recently we have the lattice-based ones, and there's a recent line of work building accumulation from the hash-based ones, such as ARC. And the focus of all these papers is basically to reduce the recursive overhead and build a prover-efficient IVC or PCD. And sort of the point which is overlooked in all these papers is the verifier complexity and the proof size. So I want to go through the concrete example of Nova, just get a good understanding of what I actually mean by that. So because I was using the term trivial NARC, I thought, it wouldn't hurt to have a slide for it. So when the prover sends the whole witness to the verifier, we just call this a trivial NARC. And verifier, given both the instance and the witness, can run the NP statement verification itself. So Nova builds an accumulation scheme for the trivial NARC for the R1CS language, such that if n is the size of the language, meaning it's the size of the instance plus the size of the witness, then the accumulation scheme that Nova builds has the following properties. So all the accumulator size, the prover time, and the decider are all going to be linear in n. And finally, the verifier circuit, which is indeed the focus of Nova to optimize, is quite efficient. It's constant size, and it's only 2 or 3 scalar multiplications. However, when you compile this accumulation scheme with a BCLMS compiler, you get an IVC scheme which has linear size proof, linear prover time, and linear decider time. And if you want to know what this linearity really means in practice, so if you got your step function f, which is just 1 million constraint, which is not even a lot, the IVC proof size, which is the accumulator size, that's going to be 80 megabytes. And the IVC verifier time, which is the decider time, that's going to be 4 seconds. That was basically 4 seconds on my laptop. And earlier Nova and recently Macronova proposed a solution for it. And the solution at a high level is that you run an additional ZK snark at the last step of IVC. However, it happens that this additional layer of ZK snark has a 24x prover overhead. I think that part of it is all right, but the part which is not all right is that it's no longer incremental, so it's not really useful for PCD. And it basically really applies to most of the accumulation schemes that we have heard of, meaning that they all have linear accumulator size, prover time, and decider. And when you compile it in with the BCLMS compiler, everything's going to be linear again. And really, it applies to Nova, Hypernova, the lattice-based ones, and the recent hash-based ones, such as ARC. So the main motivation for KZH-Fold paper is to build an IVC or PCD with sublinear proofs. And next, I want to really demonstrate why it is actually a useful primitive, what are the actual applications. So when we do distributed proving with PCD, when one party wants to hand over the computation to another prover, they basically send a PCD proof. And the second prover has to verify this PCD proof just to make sure the other prover was not cheating, which is just wasted computation. And now if you use a linear size accumulation scheme such as Nova, the size of the PCD proof is going to be large. And as a result, the wasted computation for the second prover, that's going to be large as well, just to verify the proof is valid. And if you want to see some more concrete applications of distributed proving, so one application that we actually demonstrate in this paper is called distributed signature aggregation. So the whole bug proposing for Ethereum at a high level looks something like this, where you got a tree, and at the leaves of the tree, you got the signatures from the validators, and through a number of layers, you would recursively aggregate these signatures until you get a signal signature. And as you may see, it's very much like the model of PCD. So the way we model it with PCD is that we would, at the leaves, we would have the signature verification. And then through the internal nodes, every internal node would basically verify the computation of its children. And we concretely instantiated for the BLS signature, which is used for Ethereum. And concretely, we basically use the Ethereum parameters. Another more interesting application is distributed proving. Distributed proving is basically secure data aggregation. So imagine we got a central server like Google, and we got a number of clients, such that every client has a piece of data, and Google is basically interested in the some of the client's data without actually learning anyone's individual data. And it's got real-world applications like federated learning, and it's already deployed by Apple and Google. So one model to secure aggregation is that every client would basically encrypt their data and would send the encrypted data along with a proof of correctness to Google. And then Google would basically aggregate all these proofs. And here, again, if we use a linear size PCD, the size of these proofs will dominate client-to-server communication. And then verifying these proofs will be also quite expensive for the main server as well. And yeah, concretely, we had this paper recently that we sort of show how you can build a secure aggregation out of PCD. And there we instantiated with KZH-Fold because we really want a sublinear PCD scheme. And another interesting point in that paper is that we sort of have to visit the notion of simulation extractability for recursive proofs, including IVC and PCD. And yeah, we sort of realized that KZH-Fold, because we use fiat Shamir for it, is simulation extractable, whilst some of these famous prior accumulation schemes, such as Nova and Hypernova, were actually malleable. All right, so let's almost start the paper. It happens that sublinear accumulation is basically the key to IVC or PCD with sublinear proofs. So let's see what that is. We call an accumulation scheme to be sublinear if the size of the language LAC is sublinear in the size of the language L, and if the decided time of the accumulation scheme is basically sublinear in the verified time of the language L. And if you want to get an intuition, diagram below would be basically a linear size accumulator, where the size of the accumulator is pretty much equal to the size of the statement. And when you perform a step of accumulation and you get ACK prime, that's almost the same size as the original statement. Whilst a sublinear accumulation, when you perform a step of accumulation, then you're also somehow like compressing the statement as well. Like here, the statement pi is compressed into a smaller accumulator. So you get some sort of sing-singness as well. And again, if I go through the BCLMS compiler, which said if you have a NARC and an accumulation risk for the NARC verifier, blah, 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 then we see when we have a sublinear accumulation scheme, then it results in an IVC or PCD with sublinear proofs. Because the IVC proof is going to be equal to the accumulator size, and that's going to be sublinear in the size of the original function f, which is the subfunction of IVC or PCD, and same story for the IVC verifier as well. By the way, just a quick note is that basically every snark is a sublinear accumulation as well, but we really want to build a sublinear accumulation such that the recursive overhead is comparable to the other linear size accumulation schemes. So yeah, basically any snark would be a trivial one. So going through the contributions in this paper, we built KZH-Fold, which is a sublinear accumulation scheme, and building on that, we built IVC and PCD with sublinear proofs. KZH-Fold itself is basically based on KZH, which is a new polynomial commitment scheme with optimal opening, and that turns out to have like a lot of cool applications as well. I'll give you a summary of the properties it's got. And finally, as an orthogonal contribution, which has nothing to do with KZH-Fold, we introduced a new approach to designing non-uniform IVC or PCD. And our non-uniform PCD is basically the first prover-efficient non-uniform PCD. And it has nothing to do with KZH-Fold. It's fully generic over any choice of polynomial commitment scheme, and it doesn't even use homomorphism, so you can basically use it with ARC. All right. Our goal is building an IVC with sublinear proofs and decider. And we saw that it basically suffices to build a sublinear accumulation scheme. The observation in the paper that we have is that as long as we have a polynomial commitment scheme with sublinear opening, then we can build a sublinear accumulation scheme from it. So our new goal would be basically come up with a suitable polynomial commitment scheme which has sublinear opening. So our starting point to build KZH is Hyrax. So Hyrax is this polynomial commitment scheme with a square root opening and commitment size. And if I want to tell you how Hyrax works at a high level, we basically put the polynomial evaluations or polynomial coefficients in a matrix of size square root times square root. And then we also have a Peterson setup such that its size is equal to the size of the row. And then to get the commitment, we basically commit to each row separately. So we get C sub 1, which is commitment to row 1, all the way to C sub k, which is commitment to set k, to the row k. And then the set of all these CIs would be basically a commitment to the whole matrix. And as you may see, the commitment size is a square root, meaning once you perform a single step of homomorphism between two commitments, that's going to require square root group operations as well. So I told you, given any polynomial commitment scheme which has sublinear opening, you can basically build sublinear accumulation schemes. But are we done? In fact, no. If you try to directly build an IBC scheme from Hyrax, then the recursive overhead would be basically too large. Because if I want to give you the intuition, we use the protostar compiler, and using the protostar compiler, in the recursive overhead, you have to take a random linear combination between two commitments. And that's basically what Hyrax requires square root group operations. So it's not fully practical. So our goal here would be basically come up with a similar polynomial commitment scheme such that the commitment is only one group element. All right, let's see how we can build KZH, which is KZG plus Hyrax. Yeah, we sort of came up with the name KZH because KZG plus Hyrax, and then we realized it's actually the initials of the authors. Like George was a K. I don't actually recall George's last name, and I don't want to like mispronounce it. Arancha was Arancha Zapico, and me was like Hossein Hafezi. And we couldn't basically include Benedict because he was a B. So giving you an overview of KZH2, similar to Hyrax, we would put the polynomial coefficients or the polynomial evaluation points in a matrix. And then this time we have a SRS similar to the SRFs of KZG, and then we would commit to the whole matrix in one group element C. And then similar to Hyrax, we would also commit to each row separately as well. So we have this set of DIs, which is one commitment to the polynomial, and then we have C, which is the actual commitment. And then we design it somehow that via pairing, you can actually prove that C and the DIs actually correspond to the same matrix. So the KZH opening would be basically just a set of DIs and a Hyrax opening corresponding to DIs. And then KZH verification is first checking that the C and the DIs are indeed consistent, and then basically running the Hyrax verification given the Hyrax opening. And if you want to see the efficiency of KZH2 for a multilinear polynomial f on a Boolean hypercube of size L, the commitment time is basically 2 MSMs on the polynomial. Proof size and verified time are all both square root, and opening happens to be linear field operations. And I want to emphasize that it's basically optimal, meaning that you're just doing polynomial evaluation and there's no group operations. Which makes it like perfect if you really want to commit to a polynomial once and open it at many points. And then we also extend this model of putting everything in a matrix also to a tensor, as like we come up with a generalization of KZH2, which is KZHK, that we use a tensor of degree k instead of a tensor of degree 2, which is a matrix. For example, a cube would be a tensor of degree 3. And the point of KZHK compared to KZH2 is lower verification cost at a higher cost of commitment. An extreme case of KZHK is basically when k is equal to log L. So if I want to tell you the costs for the KZH log L, the opening cost is basically quasi-linear. The opening cost is square root, and the verified cost will be logarithmic, which is better than KZH2. And yeah, if I want to really compare KZH with the prior work, it's really comparable to Dory, whilst they really both have square root opening and logarithmic proof size and verifier time. However, if you really try to build an accumulation scheme from Dory, because it uses target group operations for the verifier, then it means you have to do target group operations in your verifier circuit, in your recursive overhead, which is just basically not practical. And that's why initially we had to come up with KZH. And in parentheses, I just want to go through like a bunch of cool properties that KZH has. So KZH offers free opening for points in the Boolean hypercube, meaning that the same polynomial commitment, you can see it also as an efficient vector commitment instantiation. And also, it has a very efficient zero-knowledge compiler. And if I want to talk more about this property of free opening at Boolean points, so there was a paper recently, HydroProofs, the author is sitting right there, actually. We're just talking about it. So they basically realized this primitive that you have a polynomial commitment scheme such that you can open all the points in the Boolean hypercube for free. Is basically quite efficient, and they come up with a number of applications for it. However, their approach compared to KZH login is that they do not support the square root proof size, and they do not support this zero-knowledge compiler. Another application of this like free opening at the Boolean points that we really like took it to extreme in these papers, recent papers, Irondick and Agon, is that we basically build a dictionary commitment via polynomial commitments, and then we really need this property of free opening to open the labels efficiently for the dictionary. If I want to tell you like how crazy efficient it is, with Agon we commit to a dictionary of size 100 billion, and we get an opening of 10 milliseconds per label, which is, thanks to the efficient zero-knowledge compiler of KZH and the free opening. All right, parenthesis closed. Let's actually get into KZH-Fold, which is the main focus of the paper. So KZH-Fold is basically an accumulation scheme for the KZH verifier. Because we got just so lost, I'm going to be reviewing everything again. We wanted to build an IVC or PCD scheme with sublinear proofs, and that basically requires building a sublinear accumulation scheme according to the BC11's compiler, as we saw. And we have already built a polynomial commitment scheme with sublinear proof, and next we want to try to build an accumulation scheme for this polynomial. And we'll later see how we can basically build IVC or PCD given the PIOP and the polynomial accumulation. So I don't want to get into details of KZH-Fold. KZH-Fold is basically using Protostar compiler to build an accumulation scheme for the KZH verifier, such that the accumulated size will be square root and the decided time will be square root as well, whilst the verifier complexity, which has to be implemented in the circuit, is pretty much comparable to Nova. And then we also extend this to KZH-K-Fold as well. So we build an accumulation scheme for the KZH-K-Fold verifier as well. And if I want to be comparing KZH-Fold with a prior work, we see it's pretty comparable to Nova, as like the recursive overhead is only a single extra group operation, whilst both the decider and the accumulator are sublinear. All right, next, let's see at a high level how we can get IVC or PCD from a polynomial accumulation scheme. So the BCLMS compiler said NARC plus accumulation scheme for the NARC verifier equals IVC or PCD. And that basically applies when the NARC is sync-synced as well, meaning if it's a SNARC and you have accumulation scheme for the SNARC verifier, that's also going to be IVC and PCD, but this time it's going to have like sublinear proofs, meaning it's going to be sublinear IVC or PCD. And then we also know that as long as we have a PIOP and a PCS, then we can compile it into a NARC, and we call this a SNARC if both the verifier for the PIOP and the PCS are sync-synced. And then the thing we do in the paper is that we build an accumulation scheme for the PIOP verifier, an accumulation scheme for the PCS verifier, and that would basically give us an accumulation scheme for the NARC or the SNARC verifier. So concretely, we use Spartan as the underlying PIOP, and we use KZH as the PCS, and Spartan plus KZH is basically a SNARC. And then we build an accumulation scheme for the Spartan verifier, and we also build KZH-Fold, which is an accumulation scheme for the KZH verifier. And it would basically give us an accumulation scheme for the verifier of Spartan plus KZH. And the recursive overhead of like Spartan plus KZH-Fold looks something like this, where we have to implement both the PIOP verifier and the PCS verifier. So if you have like the circuit of Nova on the top of your head, you may realize that's way simpler than this one. And the reason is that Nova directly builds an accumulation scheme for the NARC, whilst we have to build accumulation scheme for the PIOP and the PCS separately. That's why it's a bit more complicated. All right, seeing some numbers. For the same circuit of like 2,000 Poseidon hashes, if you want to compare KZH-Fold with Nova, the prover is basically only like 3x worse, whilst the verifier is 50x better, and the proof size is 2,000x better. All right, the final section of the talk, I want to talk about this new paradigm in design of non-uniform IVC or PCD. How much time do I have?
5 minutes, including questions.
It's all right. Because I got another talk as well, so I have to manage the timing.
I mean, now it's 5 o'clock.
Oh, we started 5. Yeah, we started 5.
No, it's all right.
late, so, yeah.
It's all right. The other one needs only 15 minutes. I'll make it quick. So the standard definition for IVC's PCD is only a repetitive computation of a function f, right? But what we have really multiple functions. And you can imagine, like, in every step of the computation, instead of a single function f, we might be executing one of these like predefined instructions, FIs. And the motivation for that would be like a verifiable CPU. So Supernova defines this primitive, and they build the state-of-the-art for a non-uniform IVC. And if I want to tell you at a high level how it works, is that they keep m different accumulators if you have m different instructions. Like if your CPU has like 64 instructions, it requires 64 different accumulators. And once you want to execute an instruction, you basically just accumulate it with the corresponding accumulator, and the remaining accumulators are untouched. And the point of that is like the prover cost at every step only grows with the instruction you executed, and not with the total number of the execution instructions. If you want to see a cute diagram, it basically looks something like this. So you got 4 instructions, you're executing instruction 3, only accumulator 3 is updated, and the rest of the accumulators are untouched. But it doesn't really work for PCD, because imagine you want to do the Supernova style for PCD. In the internal nodes, you're basically accumulating 2 sets of non-relaxed accumulators, and it means that the prover cost is going to grow with the size of the instruction set. And it's quite bad, for example, if you want to do a ZKVM with it, prove a ZKVM with it, as like when the first prover hands over the computation to the second prover, now it has to send 64 PCD proofs this time, and the second prover has to verify all these 64 proofs separately. And that's because Supernova has a different accumulator per instruction. Whilst our idea is that we basically see that polynomial accumulation is way more flexible than circuit accumulation, because different polynomials of different degree, you can just imagine that the same polynomial with padding, like one just has the coefficient 0. Whilst if you have different circuits, like there would be like 2 different R1CS languages. You cannot really pad one to become the other. And our approach is that we translate each function fi into a number of polynomial constraints via the PIOP, and then these polynomials can be accumulated even though the initial functions fi's were not identical. And that's because basically polynomials are homogeneous constraints. And if I want to compare our non-uniform PCD scheme with the prior work, which is Supernova, Protostar, Kilonova, we see that for all of them, the prover time, verifier time, and the witness size, which is basically the communication, grows with the combined size of all the instructions, whilst for our scheme, which we call Spartan plus PA, it really grows with the maximum size of all the instructions. And you can basically instantiate it concretely with KZH-Fold as well to get better efficiency. Thank you.
Okay, if you don't mind taking time for your next talk, we can take.
No,
some
it's like 15
questions.
minutes.
Yeah, thanks. I'm wondering, you mentioned like for KZH, you can get vector commitment for free at Hypercube. I want to learn more.
For KZH2, it's actually pretty simple. Like I told you, we have like these DIs, right? And you can imagine like, I don't know how to explain it, but like the opening for every point would be just like the set of DIs and a row of the matrix. That would be basically just it. For KZHK, it's a bit more complicated, but for KZH2 is quite simple, as like the set of DIs and a row of the matrix. Because you just read it from the memory, you don't compute anything. Like for Merkle trees, like for a Merkle tree, when you want to like open a leaf, you just read something from the database, right? You don't really compute anything, you don't really hash anything. You just read some certain indices from the database, and that's what I mean by free.
You mean you already pre-compute?
Exactly, everything is like pre-computed before once.
Okay.
Yeah.
Any other question? Do you have any thoughts to hope of getting the SRS smaller? Right. I think that's the only thing. Is that the main thing you think to improve in that there's to improve in KZH?
Maybe, because when we wanted to do this like transparent dictionary papers, it wasn't really the problem because we did sharding. Like we commit to each shard of the polynomial separately. Like we have an SRS which is like 64 gigabytes, and then when we want to like commit to the whole database, which is like 10 terabytes, we just commit to each shard separately. But I feel like if we get like a square root SRS, that'll be so cool. Something like Dory, but like having good properties of KZH as well. Yeah.
Okay. All right. So let's thank Hossein and